guys, this is the third video on quantum numbers in chapter 6. Now quantum numbers are numbers that represent, they help us kind of make it easy to represent the different things going on in the quantum mechanical model of the atom. So there's 4 quantum numbers. I'm just going to go over them real quick and then we'll talk about what each one means. Now the principal quantum number is just like Bohr's orbits. There it represents. So what we're going to do is we're going to look at those orbits and then we're going to go a little bit farther into them. But remember when we talked about the Bohr model, we had the nucleus and we had the different orbits around it, right? Well, each one of these orbits are represent an n value, 1, 2, 3, 4, 5, and so those are the same. These are the energy levels for the different orbitals. So the values of n, any number greater than or equal to 1, any integer greater than or equal to 1. The next quantum number is the azimuthal quantum number L. Now L represents the different types of orbitals. There's 4 different types of orbitals. They all have a different representation. And so L can be any number from any integer from 0 to n minus 1. So if n is 1, L can only be 0. If n is 2, L can be 0 or 1, so to speak. Now we'll talk about the different shapes here in just a moment, but that's the shapes, the different types of orbitals. That's what L represents. And finally, for a orbital, we get the magnetic quantum number. And what the magnetic quantum number represents is the 3D orientation of that orbital. For example, what we'll see here in just a second is that we have something called a p orbital. Now p orbitals kind of look like a propeller, okay? And we can have 3 different ways for that p orbital to be oriented: the px, the py, and pz. Now they're all simultaneous, of course, but it's 3 different ways for electrons to orient themselves around the nucleus in this shape away from each other, right? Electrons are negative, we don't want too much repulsion, and so we have those 3 different ways. And what we'll see here in a second is that L equals 1 for the p orbital, tells us it's this shape, and so M sub L can be -1, 0, or 1, describing the 3 different possibilities for the p orbitals using those numbers. Now, I mean, -1 is arbitrarily assigned to the px in this case, but you get the idea that these numbers are representative of the 3D model of the quantum mechanical atom. Now let's go over the different shapes. So the easiest, most basic shape we have is the s orbital, the s subshell. Okay, there's only one type of shape, or there's only one orbital in the s, and that is this spherical thing. Now one thing, the n, the energy level, that's the principal quantum number, and we call that the shell. The L, the azimuthal quantum number, this is the subshell, which tells us what kind of orbital it is, and then the M sub L tells us the orbital. And the orbital is each different orientation, each different type, or each different 3D representation, orientation of the subshell. You can see for a sphere, we can rotate it along the 3 axes any way we want to, and we can't get anything different. It's a sphere, and we can't get those electrons away from each other, the ones that are in this orbital. Now each orbital, any singular orbital can hold 2 electrons. So in the S subshell, there's only 1 orbital, and it can only hold 2 electrons. And as we can see, in the different energy levels, we have an S always, right? So this is the first energy level, the S there, the second energy level, the S there, the third energy level, the S there. Between the different energy levels, there is a node. What a node is no electrons can exist in there, and which is consistent with Bohr's model. Remember, Bohr said that electrons can't exist between energy levels, and we still can't have that. Going up to L of 1, we get a p orbital. And again, those p orbitals looks like a propeller. We have 3 different orientations for that propeller. that p orbital can be in. And again, this gets the electrons away from each other. There, we have 2 electrons in each orbital here. So the p subshell can hold 6. Subshell can hold 6 total electrons. And we have 3 different orientations, making sure that those 2 electrons in each orbital are not in the same space. We don't increase that repulsion. Next one up is the L of 2. Remember, L represents the subshell. It tells us what type of orbital it is. L of 2 tells us it's a d orbital, and there's 5 different possibilities. Now remember, so this is L of 2. Okay, and so M sub L can be -2, -1, 0, 1, or 2. Any number from -L to +L. And we've got 5 different numbers here, and we've got 5 different orientations for the d orbital. Again, making sure that they're away from each other, that the electrons don't increase the repulsion by being in the same space. Okay, so the d subshell can hold 10, 2 electrons in each of these, so 10 total electrons. Finally, we have the f orbitals. Here's what they look like. We have 7 possibilities, 14 total electrons, same type thing, and this is the L of 3. Now it is important to note that all of these things are simultaneous. We fill these orbitals with electrons simultaneously at the same time in the same atom. But as you can see, the orientation of the different subshells makes sure that no electrons are in each other's space. So minimize the repulsion. Okay, maximize the distance between orbitals and minimize the repulsion. Finally, we have the spin quantum number. So we have 2 electrons in each orbital, and we have the spin quantum number that denotes the spin of an electron. And 2 electrons in the same orbital have different spins. Okay, so 2 electrons in the same orbital have different spins. And so what this means is that no 2 electrons can have the same set of 4 quantum numbers. So what that tells us is that no 2 electrons can have the same energies, because they have different energies based on their spin, based on the orbital, based on the subshell, based on the energy level. And so you can think of these quantum numbers as coordinate numbers almost, right? Like coordinates, like geographical coordinates. We have the n, which is the roughest estimate of where that electron is. It tells us just the energy level. Then we have the L. The L tells us the shape or the type of subshell, S, P, D, or F. And so that tells us, well, it's in this subshell in one of the orientations of that subshell. For a p orbital, it could be the px, py, pz, but it's in a p subshell. The m sub L tells us which one it is, the px, the py, the pz. Now remember, within each orbital, there can only be 2 electrons. And so the spin quantum number tells us which way that electron is spinning, and it lets us identify a singular electron. And so no 2 electrons can have the same set of 4 quantum numbers. This will lead us to electron configurations in the last video in Chapter 6, which is the big part that Chapter 6 has been leading up to the whole time.